In this video, we move on to section 3.7 of Greenberg's, pages 113 through 141. The topic is, we're still on higher order ODEs, and now we'll look at the non-homogeneous cases. So the topics that I'd like to go over in the video is first, talk about a little bit more about the general solution, and that again is the sum of the homogeneous solution as well as the non-homogeneous solution, which we'll denote as Y sub NH. We'll talk about some of the key requirements of the sort of ODE that we'll solve in this section, and then I'll walk you through a step-by-step method, looking at an example, again taken from Greenberg. Your objective here will be your ability to solve many, not all, but many non-homogeneous cases with constant coefficients, and that's another key requirement that we'll cover here. And this is for an ODE of any order, so any arbitrary order. Now remember, the general linear non-homogeneous ODE can be expressed in the following form. That is, if we set the nth derivative of y by itself, we can describe the other derivatives as being multiplied by coefficients, generally functions of functions of x, times the lower derivatives. And I got to remember to put the derivatives in parentheses in the superscript, all the way down to the first derivative, and then finally the zeroth derivative, or just y itself. And for a non-homogeneous case, the right-hand side, which is where we put all the parts of the equation that are independent of y, and that part is non-zero, so that makes it non-homogeneous. And just so you remember, we also describe this general equation as the linear differential operator, capital L, and it's operating on y. So we could write this same equation as capital L square bracket y is equal to our right-hand side. And our right-hand side is also refer to that as the forcing function. In many systems or many applications, this acts as a forcing function to drive the action of y versus x. So let's go back and review some aspects of the general solution. And this pertains to theorem 3.7.1 of Greenberg. And you recall, we've talked about this before when we were looking at the non-homogeneous case for the first order ODE, and we established that the general solution is equal to the part of the solution that gives 0 on the right-hand side, or the homogeneous solution, and the part that gives the non-zero part on the right-hand side. So here YH we'll refer to that as the homogeneous solution. That is, if that solution is operated on with our linear differential operator, we'll get 0 on the right-hand side. And then we also have the non-homogeneous solution, which, when operated on by the linear operator, we get the forcing function. And oftentimes, actually more typically, this is referred to as the particular solution. But you should note that this is not the same particular solution as you would get when you satisfy an initial condition or a boundary condition. It's the same words, just used for a different meaning. So it's not the same as the case of solving an initial condition IC or boundary condition BC. So again, this is the general solution. And because it's a linear operator, so if we operate L on the general solution, which again is the sum of the homogeneous solution and the non-homogeneous solution, because the operator is linear, we can just, that's equal to L operated on just YH plus L operated on just Y, the non-homogeneous solution. And again, when L is operated on the homogeneous solution, we get 0. And when L is operated on the non-homogeneous solution, we get F. So this breaks down, this is sort of an explicit illustration of the two parts of the solution, one part giving 0 and the second part giving F, and the sum of those solving the full equation. Now this explicit decomposition of the solution allows us to address another concept, and this is discussed in theorem 3.7.2, and that is, suppose we impose a number of different, or we have a number of different types of forcing functions that are applied. And let's say we apply them individually. So we're going to apply these different forcing functions individually. So say first we apply again to our system forcing function 1, and then we apply forcing function 2, for example, and we could apply these different functions, and we would get the solutions for, or the responses, after we apply each of these functions. And so the solutions would be YNH1, YNH2, all the way out to Y non-homogeneous 3. So these are the, non-homogeneous sub K. So these are the non-homogeneous solutions to these different forcing functions. Of course, each general solution would share the same homogeneous solution, but again, they would have these different responses to the non-homogeneous part. And so we could also apply all the forces all together. So first we applied them individually. Now let's look at the effects of applying them all together, in which case we would solve L, again our linear differential operator, being equal to F1 plus F2 summed all the way to Fk, And the effects are additive on the solution. So the effects of applying all the forces together are additive on the solution or the response. And this is a property of this linear system. So again, the general solution always has the homogeneous solution, but the effects of the individual forces are to add their individual non-homogeneous solutions. And those individual non-homogeneous solutions are additive. Okay, so this is a result of the linearity of L. So these are some key concepts you'll need to understand, I guess some preliminaries. So now let's talk about how to actually solve some cases.